Here I want to solve this logical mathematical puzzle. Let me start by reading it and then we will dig deeper and try to understand more about the content of this puzzle. So, an old puzzle goes like this. A traveler travels 1 kilometer straight south, where he turns and goes 1 kilometer straight east. Then there he turns again and goes straight for a kilometer north. He arrives back where he started from. There he finds a bear. What color is the bear? The traditional answer is, of course, white, because the traveler had to leave the North Pole. However, someone realized that not only the Arctic meets the given conditions. Then the last part of the problem is not properly phrased here. Let me rephrase it a little bit. Can we imagine any other point on the globe from where it is 1 kilometer south, then 1 kilometer east, then north, and after a journey, the person returns to their starting point? And the answer is, of course, that we can imagine another point on the globe and where we can play this kind of game. So let's start from the North Pole. So I will sketch the Earth like a sphere, and then if you think about it, if we start at the North Pole, we go 1 kilometer south. So this is 1 kilometer. Then we go 1 kilometer east, and then if we go back 1 kilometer north, we go back to the North Pole because this is the northern direction, just like this one. So we have 1 kilometer, and then we go back 1 kilometer. So you can think, for example, of spherical coordinates if you are mathematically inclined, and this is quite a simple reasoning to carry out. However, there is also another possibility, and there's more than just one. We will focus mainly on one if you want, but I will try to let you understand what the other possibilities might be. So, what I'm going to do is I'm going to draw a circumference here near the South Pole in this case, and this circumference is such that its perimeter is equal to 1. And let's assume that this is the center of the sphere, for example. Let's call it C. And we can connect the center with a point on this circumference, and then we can also draw the z-axis, which passes, of course, through the point C. And then we have the polar angle, which is phi. So we call it phi. And this is the radius of the sphere, which is also the radius of the Earth. Of course, the Earth is not exactly a sphere, but we are going to assume in this problem that's the case. So the Earth will be depicted as if it were a perfect sphere. And of course, for example, this would also be equal to r, for example, and so on. If we calculate r times the sine of this angle phi, this would be the radius of this circumference that I have drawn. And if we multiply by 2 pi, this would be the perimeter of that circumference, and we assumed that the perimeter was equal to 1. So if you want, we can also rewrite this equation as r times sine phi equal to 1 over 2 pi. And if you think about it, the radius of the sphere, the radius of the Earth, is very large. It is of the order of 6,000 kilometers, more than that, something like that, right? So it's very large, but this number is not really large. It's smaller than 1. So when we multiply this r by the sine, we assume that the large radius will be multiplied by a small number because otherwise we would not be able to get 1 over 2 pi. So this means that this sine is small. And if the sine is small, it can be approximated with the angle itself, which is phi, right? And therefore, r times phi is equal to 1 over 2 pi. But r times phi is also equal to, if you think about it, this length, and let me change the thickness of this pen. It is equal to this length, and it is also equal to, I mean, I'm connecting this point here with this point here, and if you want, it is also equal to this length, if we think that, so if we connect C with this point on the circumference, and we can make a similar reasoning because this angle would be phi. So you can try to understand it. It's not complicated. So it's not complicated at all for symmetrical reasons. So you have the symmetry in the problem is a spherical symmetry. So r times phi will give us this length. And now let's assume that we start from a point in here, which is located in the northern direction with respect to this point, and this length here would be 1 kilometer. So if we start from such a point and we move downwards by 1 kilometer, and when I say downwards, I mean south, then if we move eastward, since the length of the circumference here is equal to 1, and we want to move by 1 kilometer, so we move 1 kilometer downwards, so in the southern, towards the southern region, so southward. Then we move eastward by 1 kilometer. I mean, it's easy to understand that we go back to the initial point here of the circumference, and then if we go back up, so if we go northward in the northern direction, we go back to the initial point. So this is exactly a point that satisfies the requirement of the problem. It means that we are starting from a point here whose distance from the South Pole is equal to 1, this one here, which is this length, and we are moving on the sphere, so we have to measure our lengths on the sphere. So this is a non-Euclidean geometry, if you want. And then we have to add this length in red, and we have already calculated it because r times phi is exactly that length, and it is equal to 1 over 2 pi. And if you want, this is an approximation symbol, so it would be approximately equal to. But since r is very large, the sign is approximately equal to phi. So we get 1 plus 1 over 2 pi. It's a point that satisfies the constraint. And of course, you can take all the points in a, let's say, spherical symmetry. So you can move around this circumference here, and all those points are okay. But there are also other possibilities actually, and in particular, if we choose a point which is closer to the South Pole, we can, so for example, we can choose a circumference closer to the South Pole such that the length of this circumference can be chosen equal to 1 over n, where n is an integer. And if you think about it, if we choose a length of this kind, when we move around by one, so when we travel 1 kilometer on the circumference, we are going to travel along the circumference n times. So we complete n revolutions around the circumference. So you can rewrite the equation here, for example, like this. So you have 1 over 2 pi n, and similarly here you have 1 over 2 pi n, and then you can start from a similar point, from a point which is similar to this one, but of course in this case we are at a distance of 1. Now it's I mean the drawing is becoming messier and messier, but I hope you understand. For example, we can start here 1 kilometer from this point of the circumference, so this would be 1. Then we move around n times, and then we go back up. And this is also a point that satisfies the constraints. which is located at 1 plus 1 over 2 pi n from the South Pole. Now, you can understand that if you let n to be a very large number, we are getting closer and closer to the South Pole. So the circumference would be closer and closer to the South Pole. And at a certain point, we find that this ratio would be close to zero if n is very large. And therefore, it's as if the circumference becomes a single point. This problem is interesting, especially because it started as a simple puzzle, and it is actually an old puzzle. I don't know what this old means, but I guess that it refers to centuries. I don't know exactly, because I found it in a book. Initially, this problem was thought to give a simple answer. So, in particular, the answer would have been white, because the only possibility, without thinking too much about the problem, was this one. So, we start from the North Pole, then we go downward in a southward direction. Then we go eastward by 1 kilometer, and then, of course, we go back to the initial point if we go northward. So if we go in the northern direction by 1 kilometer, so we go exactly back, simply because of the non-Euclidean geometry and using the simple properties of spheres, of spherical symmetry. But as you can see, there are other possibilities, and these are the other possibilities.